Hello, my name is Chen Kim, and I'm here to present robotic interestness via human-informed visual object detection. So we are interested in autonomous exploration for robots. Especially we are interested in interesting scene recognitions, which is good for planning and decision-making for robotics. But the question is, what scenes are interesting? The scenes, the the above are not interesting, and the two images below are quite interesting to the dataset, to the robots. So there have been various works that try to define and model visual interestingness, but the concept of visual interestingness is inherently subjective and non-trivial. There have been various works that try to model, including saliency, memorability, novelty, and anomaly. More recently, there have been work on online visual interestness, which is the work that define the interestness by the ability to adapt to environments quickly and detects interesting scenes online. It loses interest over repetitive scenes. This is the diagram of visual interestness, which is composed of three stages: long-term, short-term, and online. The core idea is that the long-term memory and short-term memory enables the robots to adapt to environments, and whenever the robots see unfamiliar or novel scenes, it detects those scenes as interesting. So the motivation of our work is that the previous approach is an unsupervised method of detecting interesting scenes, and it loses interest over repetitive scenes even if they are similar. But there are some limitations. Number one, it cannot adapt to human-informed interesting objects. The challenge is that before a mission starts, both the robot and human operator does not have any information about what the interesting objects will be. So the traditional object detection methods that is pre-trained on the predefined class of objects are not applicable to these situations. So our idea is that we use fusion object detection approach to learn human-informed interesting objects. Comparing traditional and fusion object detection, while the traditional object detector uses abundant dataset and annotations to train object detector, the fusion object detector only uses very few label examples to train fusion object detector. The model that we are using in this work is the TFA, the fine-tuning based fusion object detection, which is composed of two stages. In the first stage, it base trains the base class of images using abundant data sets, just as traditional object detections. But in the second stage, it uses fine-tuning. It freezes feature extractor. It only fine-tunes the final layer, and to fine-tune the final layer, it generates mini batch by mixing base class images and novel fusion images. And it takes quite quick time to train because it only fine-tunes the last layer. So this is the method. We call this error interactions. If you see on the left side, the robot explores the environments. And when the robot perceives some scenes, it goes through the visual memory module in the robot that processes the interestingness of the scenes. And the robot selects potentially interesting images, and the robot sends those images to the human operator sitting at the base stations. The human operator on the right side base stations should give feedback stating whether the image is interesting or not interesting. When the human operator thinks the image is interesting, then the human operator should draw the bounding box of the specific objects in the scene and the specific labels and the annotations of that specific image is being fed into the fusion object detector to fine-tune the last layer. This is what's happening in the actual deployment. When the robots explore the environments, it detects some interesting scenes. Interesting scenes appear on the left side of the work, and the human operator, if the human operator thinks that the image is interesting, it draws the bounding boxes around the images, and it is being fed into the fusion object detector to train novel classes. There are some techniques to mention. We use the weighted mixture of mini batch for learning, which is when generating a mini batch for fine-tuning training. The previous work, TFA, only used base images and the combination of base images and novel shots. In this work, we increased the frequency of using the novel shots when generating mini batch. So when the R is the ratio of using the novel shots. When our assumption is that if we increase the ratio R, it accelerates the learning of fine tuning. For the evaluation, we used 4 datasets: Subti Tunnel, Subti Urban, Scott Reef, and Drone Filming. And for baseline and metric, we compared our method with TFA, the object detection performance, with different parameters. We also measured the performance within 5 minutes and online responsivity. The results is that we compared our model with the TFA, and our model, there are 3 types: R1, R2, R3, which is the ratio of using novel shots compared to the base shots. So when we use R2 or R3, we observed that our method, our error interaction method outperforms TFA methods. What you see on the right side is the best performance of object detection on each class of objects. This is another results for object detections. So we constrained time constraints, because we wanted 5 minutes online deployment robot explorations. So we wanted very quick learning of fusion object detector, and we saw that within 5 minutes, the fusion object detector were able to achieve some good performance within 5 minutes. And lastly, this is the online responsivity that compares our method versus the previous work. Yep, this is the end of the presentation, and thank you for listening.